In this episode, we move into a skill that sits at the center of trustworthy AI, testing. Testing is how an organization proves, with evidence, that an AI solution behaves acceptably before it is trusted to influence real decisions. For brand new learners, it helps to think of testing like a driver's license exam, because a person can claim they drive well, but the world needs proof that they can handle normal roads, unusual situations, and safety rules. AI solutions need a similar demonstration, because a model can appear impressive in a lab, yet fail when faced with messy, real-world inputs, or it can behave well for most users while creating unfair outcomes for a subset. Domain 2E asks you to test across 4 pillars that often overlap, but must be evaluated distinctly: accuracy, robustness, bias, and safety. The goal is not to become a specialist in training algorithms, but to understand what these pillars mean, why they matter, and how testing is designed at a high level to reveal weaknesses before customers experience harm. A testing mindset is also about humility, because it assumes systems can surprise us, and that trust must be earned repeatedly, not declared once. By the end, you should be able to explain how an evaluator designs tests that are meaningful, realistic, and connected to real risks, rather than tests that only produce flattering metrics. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Accuracy is the first pillar, and it is the one most people think of first, but it must be defined carefully because accuracy is not one universal concept. In simple terms, accuracy is how often the system produces the correct output for the use case, but correctness depends on what the output represents and what counts as correct in practice. For some systems, correctness is a clear label, like classifying an email as spam or not spam, while for others it is more complex, like predicting risk, recommending priorities, or generating helpful guidance. Testing accuracy begins by defining the objective and the ground truth, meaning the reference standard used to judge correctness, and that ground truth must be credible and consistent. Beginners sometimes assume ground truth is obvious, but in real organizations it can be noisy, biased, or delayed, especially when labels come from human decisions that were themselves imperfect. An evaluator therefore asks how labels were created, whether they reflect the intended objective, and whether they are stable enough to support testing. Accuracy tests then measure not only overall correctness but the pattern of errors, because a model can be accurate overall while making a dangerous kind of mistake in a specific category. The core lesson is that accuracy testing is meaningful only when it is tied to the real decision context, not when it is treated as a generic score. Robustness is the second pillar, and it answers a different question. Does the system keep behaving acceptably when conditions are not ideal? Robustness matters because real-world inputs are messy, incomplete, and changing, and people may also behave in unexpected ways once the system is deployed. A model can achieve high accuracy on clean test data and then degrade sharply when inputs include missing values, unusual formats, or patterns that were rare during training. For beginners, robustness is like a backpack that survives not only in your bedroom, but also in rain, dirt, and crowded hallways. It has to hold up in the environment it will actually face. Testing robustness often involves stress conditions, such as introducing noise, varying input phrasing, changing distributions, or simulating realistic shifts that can happen over time. It also involves testing edge cases, which are uncommon scenarios that can produce outsized harm if handled poorly, such as extreme values or ambiguous situations. An evaluator does not need to create every possible edge case, but they do need to show that the organization identified plausible stressors and tested the system against them. Robustness testing is often where hidden brittleness is revealed, because the model's confidence may remain high even as its correctness falls in unfamiliar conditions. A robust system is not perfect, but it degrades gracefully and signals uncertainty rather than failing silently. Bias is the third pillar, and it is closely related to fairness, But here the emphasis is on testing whether the system produces systematic differences that disadvantage certain groups or scenarios without legitimate justification. Bias can enter through training data, labeling practices, feature choices, and even how outcomes are measured. Beginners sometimes think bias testing is only about intentional discrimination, but most bias in AI systems is unintentional, emerging from historical patterns that the model learns and repeats. Testing for bias requires defining which groups or segments are relevant for the use case, and which disparities would be considered unacceptable or suspicious. It also requires careful selection of metrics, because average performance can hide unequal error rates, unequal false positive rates, or unequal access to favorable outcomes. An evaluator asks whether the organization tested performance across segments, whether it examined the kinds of errors that occur, and whether it assessed whether observed disparities might reflect differences in data quality or systemic factors rather than true differences in the underlying reality. Bias testing also includes checking for proxy variables, where a model appears not to use sensitive attributes directly, but still relies on correlated signals that reproduce discrimination. For beginners, you can think of a teacher who does not grade by name, but consistently penalizes students from a certain class because of a rule that correlates with that class. Bias testing is how the organization finds these patterns before they become harm and reputational damage. Safety is the fourth pillar, and it focuses on preventing harmful outcomes, especially those with high severity. Safety testing is not only about whether the model is wrong, but about whether the model can cause harm through the decisions it influences, the recommendations it provides, or the way users interpret its outputs. Safety testing, therefore, starts by identifying credible harm scenarios, including misuse scenarios and high-stakes error scenarios. For beginners, a useful analogy is testing a child-proof cap, because you are not only testing whether it opens, but whether it fails in a way that could hurt someone. Safety tests often include adversarial or boundary-pushing inputs, not to be malicious, but to ensure the system does not provide unsafe outputs when prompted in certain ways or when presented with risky conditions. Safety testing also includes evaluating how the system behaves under uncertainty, because overconfident errors can be more dangerous than cautious uncertainty. A mature safety test program includes escalation behavior, meaning the system routes or defers when safety risk is high, rather than forcing an answer that could be harmful. Evaluators want evidence that safety is built into the acceptance criteria for release, not treated as something to fix later. To understand how these pillars connect, it helps to see testing as a set of lenses, where each lens reveals a different failure mode that might be invisible to the others. A model can be accurate overall, but not robust, meaning it fails when inputs change. A model can be robust, but biased, meaning it fails certain groups consistently even when it is stable overall. A model can be accurate and robust, but unsafe, meaning it produces harmful recommendations in rare, but critical scenarios. Testing across all four pillars prevents the organization from celebrating a single success metric while ignoring a different risk that could cause real harm. For beginners, this is like evaluating a car not only for speed, but also for braking, steering, crash safety, and reliability, because a fast car is not a good car if it cannot stop safely. The evaluator's mindset is to ask what could go wrong in each dimension and design tests that reveal those weaknesses. Testing must therefore be planned, not improvised, because improvised tests tend to focus on what is easy to measure rather than what is risky. A well-designed test plan makes it hard for the system to hide its weaknesses behind averages. High-level testing also depends on representative data and realistic scenarios, because unrealistic tests produce false confidence. An evaluator checks whether test datasets reflect the diversity and messiness of real inputs, including missing values, variations, and rare categories. They also check whether scenarios reflect real workflows, because the system's output may be interpreted and acted on by humans, which influences whether harm occurs. For example, an accuracy test might show the model predicts correctly, but if the output is presented in a confusing way that leads humans to take the wrong action, quality and safety can still suffer. Bias testing requires careful attention to sample sizes and segment definitions, because small segments can produce unstable statistics, and unclear segmentation can hide disparities. Robustness testing requires variation that reflects plausible real-world shifts, not random noise that does not resemble the true environment. Safety testing requires thoughtful exploration of harm scenarios without turning testing into sensationalism or vague fear. The overall goal is to create tests that are demanding in the ways that matter, because demanding tests are what prevent customers from being the first ones to discover failure. A mature organization prefers to find its own weaknesses in testing rather than in public. Another important point is that testing should include both pre-deployment evaluation and ongoing retesting, because AI systems operate in changing conditions. Even a model that passes all tests today may become less accurate or more biased tomorrow due to drift, new data patterns, or evolving user behavior. Domain 2E expects you to understand testing as part of ongoing assurance, not as a one-time hurdle. For beginners, it is like maintaining a bicycle. You do not check the brakes once and assume they will be fine forever. Ongoing testing can be triggered by model updates, data pipeline changes, incident signals, or scheduled review cycles. Evaluators check whether the organization has a retesting plan and whether it uses monitoring signals to decide when deeper testing is needed. They also check whether the organization retains enough evidence, like model version identifiers and test results tied to those versions, to compare behavior over time. Without ongoing testing, the organization may not notice gradual degradation until customers complain. Testing is therefore both a gatekeeper before release and a guardian during operation. A common beginner misconception is that passing tests proves the system is safe, when in reality tests only reduce uncertainty, they do not eliminate it. Testing is about building confidence through evidence, and then combining that evidence with supervision and controls that manage remaining risk. Another misconception is that you can test accuracy first and worry about bias and safety later. But if bias and safety are not part of acceptance criteria, the model may be released with unacceptable harm baked in. Evaluators therefore look for integrated acceptance criteria that include the 4 pillars, not just a performance target. They also look for transparency about limitations, meaning the organization documents what was tested, what was not tested, and what risks remain. For beginners, this is like knowing the limits of a weather forecast. It can be useful even when uncertain, as long as you do not treat it as a guarantee. A mature testing program produces both results and humility, which means it encourages appropriate oversight rather than blind automation. The strongest systems are those where tests inform controls, and controls inform further tests. To make this practical, imagine an AI system that helps decide which customer complaints should be handled urgently. Accuracy testing would examine whether urgent cases are correctly identified based on a credible label, such as confirmed severity. Robustness testing would examine whether the model still works when complaint descriptions are short, poorly written, or in different formats, because real customers do not speak in perfect sentences. Bias testing would examine whether certain customer groups or regions are systematically deprioritized or misclassified, which could create unfair service. Safety testing would examine whether the system ever deprioritizes cases involving safety risk, even rarely, and whether it escalates appropriately when uncertainty is high. A strong test program would also examine the trade-off between false positives, which create workload, and false negatives, which miss urgent cases, because both affect quality and trust. It would then connect these findings to supervision triggers and escalation pathways so that high-risk cases receive human review. This example shows that testing is not a set of abstract charts. It is a way to protect customers by revealing weaknesses early and guiding safer operation. When an organization does this well, it finds problems internally rather than learning about them through public frustration. When you step back, testing AI solutions for accuracy, robustness, bias, and safety is the disciplined process of proving, with evidence, that the system behaves acceptably under realistic conditions and within important boundaries. Accuracy testing validates correctness in the context of credible labels and meaningful error patterns. Robustness testing validates that performance does not collapse when inputs shift, become noisy, or reach edge cases, and that the system fails gracefully. Bias testing validates that performance and outcomes do not create unacceptable disparities and that proxy-driven harms are detected. Safety testing validates that high-severity harms are prevented through conservative behavior escalation, and boundary checks, even when the system is pushed into risky scenarios. For brand new learners, the central takeaway is that a trustworthy AI system is one that has been challenged before it is trusted, using tests designed to reveal the kinds of failures that matter most to people. Domain 2E expects you to understand testing as a core assurance capability because it is how an organization earns confidence without overpromising certainty. When you can explain these 4 pillars and how testing reveals different kinds of risk, you are building the foundation for evaluating methods, controls, and long-term effectiveness in the episodes ahead.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.